All right, so we're going to talk about everyone's favorite topic, AI agents. And I know there's a bit of agent fatigue in the industry right now. And so I think just to start off this talk, I will just give a bit of a lay of the land from my perspective with AI. And I think that there's a lot of hype with AI. AI is extremely capable, but the capability doesn't always come with reliability, and we don't always consider responsibility in our industry right now. So there's a huge push to move as fast as we can, and I think that we have, in some cases, forgotten the lessons that we've learned from running applications in production with real users and adversarial users as well. So what I'm going to talk about today is how you can build AI agents that you can trust, and what that looks like from an AI agent architecture perspective. And we're going to use AWS as a toolkit, because I work at AWS and that's my toolkit, but you can take the patterns and apply them to any AI agent that you're building. So really quick, I just want to see, is anybody here building custom AI agents? Okay, quite a few. That's great. All right, awesome, because I think that there's a difference between building AI agents and using AI agents. And so that really changes the way that you approach it. There we go. All right, so building AI agents, this is, using AI agents, I'm talking mostly about productivity agents. So these are things like coding assistants, chatbots, end user applications. And those are the programs that we all use day to day. But there's gonna come a time where that's not going to be enough for what you need. Maybe you need to control something end to end. You need to have visibility into the execution environment. You need to be able to control the tools that are allowed to be called. And some of these systems just don't give you enough knobs to turn. So what a lot of people end up doing is building their own custom AI agent setups from the ground up. You write all the code, you set up the infrastructure, you do the whole thing. So I'm going to be mostly focusing on that today with AI-powered applications. And so that's, customer service agents, claims processing, incident response, building your own application using some sort of framework or SDK that allows you to invoke models under the hood. So whenever you're creating your own AI agents are the model plus the harness equals the agent. So the model by itself can only think, it can't actually do anything. An agent has the ability to interact with the world and react to changing situations and kind of loop until a task is done. The harness, the system you build around the agent, is what allows you to do that. So we're going to be talking about some different harness architectures and different components you could bring into your agent harness to improve reliability and trust with your agents. AI agents break in creative ways, oftentimes in ways that you may not expect or even think of as people. And part of the reason for this is because models are naive, and they don't question things in the same ways that humans do. So some of these are real examples that happened, and some of these are things that could happen. You may recognize some of these from the news, the tech news. So for example, let's say you have a customer support agent that over-refunds. So they issue a refund for the wrong amount. That might not be a problem for one time, but the problem with AI is that the problems compound because they happen at scale very quickly, oftentimes before we even have the chance to notice. Chatbots leaking data, that's another really big one, very common one. And then this one is a real one. A car dealership chatbot sold a car for $1, and then they were held responsible for selling that car. Like, no, your chatbot, he wanted to sell it. And there was another one where an airline chatbot was talking with a customer, and the customer got that chatbot to agree to something, and then it went to court. And so these things have real risks and liabilities, and it depends on your industry and your business on how much risk and liability you are willing to tolerate, and also what specific use case. So this is part of the reason why we've seen an explosion of personal productivity agents and less of deployed autonomous agents, right? I think that the promise in the industry is like the line that you hear is that we're gonna have fully autonomous agents that are doing everything by themselves. But what we're really seeing in reality at this point is more of a human-in-the-loop type of approach, where the AI is augmenting people to be able to move faster or make better decisions, but ultimately we people have to control those. So I think that the idea is that bit by bit we'll be able to architect these systems to be more reliable and trustworthy, and the way you do that is through guardrails, and there's different types of guardrails. So this is the kind of the thesis of my talk here, is that you shouldn't just trust AI agents, but you should trust the systems that you build around them. So the model is one component of a larger system, and you control the rest of that larger system. And that system is going to be deterministic in nature. The model is non-deterministic, and that is something that's new for us. We're all trying to figure out how to control that. So let's quickly go over some common agent failure modes. And I like to put these into 3 broad categories. First being that the agent says something wrong. So this would be like it promises something it can't guarantee, leaking information, hallucinating information. Hallucinating information is a really big one, that we're trying to figure out how to stop. But these LLMs, it is partially just a way that they're designed, right? Like it's something that we have to consider, that the agent can get it wrong. And I'm sure as we've all worked with AI, we've all seen this many, many times. The second bucket is that agents do something wrong, because again, models can only think, and they can talk, they can chat, they can emit tokens, but they can't do anything on their own. So once you put a harness, a system around it, you are giving that agent capability for whatever you give it, right? So this makes agents capable. It allows them to actually complete tasks. This is what makes them useful, but it's also what makes them very dangerous. So you have to be very careful about what capabilities you give to your agents. So the agent can do something wrong. Maybe it takes action against the wrong account, or it deletes data. I'm sure you've all seen the many stories of coding agents just deleting production databases within the blink of an eye, right? So why does that happen? It happens because the person gave that agent the authority to do that, or they were using it on a machine that had access keys to their production account. So, some of these things, it is, the lessons that we all learn and share. And so I'm very grateful to everybody who shares whenever something goes wrong with AI, and they come online and they write a blog about it and they out themselves about what they did wrong. And then we all get to learn from those, and we get to elevate the lessons and take them all with us. And then finally, we have the third failure mode, which is someone tries to break your system. And that's essentially trying to get the agent to do one of the things in the first 2 buckets here. So this is a lot like prompt injection, ignore your instructions. It's also about abusing your agent, trying to get it to do something that it shouldn't do. So we all have to pay for tokens. So using public chatbots for things that they were not intended for, so that you don't have to pay for the tokens, that's a really big abuse vector right now. But also with the prompt injection, it's not just about prompts. With tools, we're allowing agents to dynamically inject context coming from many different data sources, including the internet, source code, you name it. A lot of these agents have access to it, especially the agents that are running on your local machine with admin access and wide open access to the internet. So, we are exposing these agents to any piece of data on the internet. So the attack vector for that is larger than maybe what we've dealt with in the past. All right, so this is the example we're going to use throughout the rest of the talk. And let's see if this works here. Yeah, okay. So we're going to use a customer service example. And this customer service agent has access to a couple of different tools through an MCP server. MCP is Model Context Protocol, and that's a standardized way to expose tools to agents. And then we have our tools at the bottom. And these tools are things like company policy lookup, escalate to a human rep, so that's our human in the loop, generate a return label, look up an order, or check the return eligibility. So I'm going to use AWS technology to show you this architecture. And this is a very simplified version of this architecture. This is kind of the starting point, and then we're going to add on pieces as we go along here. So I'm going to be using Strand's Agents SDK, which is a agent framework. that's open source from AWS that you can use to build whatever you want. It is model provider agnostic, open source, so you can download it, use whatever model. You can even use local models and deploy it anywhere. And then Bedrock is the inference provider. It just hosts the models. Amazon Bedrock Agent Core is a collection of different services to host different components for your agents. So the agent itself, this agent is going to be running on something called Agent Core Runtime. And Agent Core Runtime is a hosted runtime environment that hosts every agent session in a isolated micro VM, and it has its own like sandboxed access there. And then Agent Core Gateway is essentially a hosted MCP server. So you don't have to run your own MCP server. Gateway has, authenticated access through MCP, and we'll go over a couple of other things that you can use from that. But again, it's more of the patterns. So I'm just explaining this so that you understand what I'm going to show you in the demo. But the main thing is the patterns that we're going to do. And then all of the tools are hosted on Lambda, which are just function as a service in the cloud. All right, so let's quickly go over just some agent code that doesn't have anything, no guardrails built into it. So here we have some Python code, and you create an instance of your model. In this case, I'm using Bedrock as the inference provider. You would connect to your MCP server. So this is a MCP server URL. It could be anything. You connect to your server, and then from there, you list the tools on that server, and then you take those tools and you inject them into your agent along with the model, and now you have an agent that you can use. Down here, this would be a CLI-based agent, and I just simply have a loop where I'm submitting a prompt, and then this would run, and it would be able to invoke the tools and interact with the user through the command line. Now, one quick note on MCP is whatever tools exist on this MCP server, with the way this is now, I just give those tools to the agent. So if at any point in time the tools list changes, then my agent gets the new tools as well. So if the tools suddenly get compromised, then my agent's gonna have access to compromised tools. So there's all sorts of things that you need to think about with this, but this is our starting point with just a basic agent that has access to tools. All right, so we're gonna take a layered approach to trust throughout the rest of this talk. We're going to talk about some deterministic and non-deterministic controls for different levels, because the agents themselves are non-deterministic, but you need to be able to have determinism in certain parts of your application. And where you can have determinism, you should. For multiple reasons. It's more auditable, it's more controllable, but also it's cheaper. So you should definitely, where you can, don't AI things that don't need AI, is my point on that. And then you want to have multiple layers of control, just like we would for any other application that we put out in the world in production, is there are multiple lines of defense, right? It's not just the perimeter. You want to have a zero trust type of environment as much as you can. So this is what we're going to be looking at here. The other note that I want to make is that the fundamentals still apply. So this is, again, something I think just is it comes from everybody moving so quickly in the industry, and we all are under a lot of pressure to ship, move faster, do more, and I think that there are times when we forget that the old lessons still apply, and an AI agent is just a new component in your architecture. It's just a new component in your application, and it creates potentially new distributed systems problems as well. All right, so we're gonna go over a couple of different scenarios, and then we'll talk about how to potentially solve those scenarios. So I don't trust users to not abuse my agent. In this case here, we have a user asking if the agent can help them solve elite code problems so that they don't have to pay for a coding agent subscription. And the agent's just like, sure, I'll get right on that for you, right? And so agents are really eager to please, especially the models that are out of the box. They really want to help. They want to be helpful assistants. And so if you ask them something without any sort of guardrails, they're just going to try to do it. They are not usually programmed to push back, except for the most recent release of Opus 4.8, which just came out, I think, 2 days ago. And that one is designed to push back a little bit more. So I think that this is something that even the model providers are trying to solve for. But you, regardless of what the model thinks, you shouldn't leave everything up to the model. So in this case here, the users are going to ask really unrelated questions. They're going to try to do prompt injection. They're going to try to bypass your instructions. They're going to try to get your agent to leak internal system details. And you need to have a way to try to mitigate that. So the fix for this is model guardrails, and this is really the bare minimum that you should have, but I am shocked at the amount of just like chatbots that I see on the internet that don't have this in place. And not every agent is a chatbot, but that is one of the easiest things for us all to relate to. And so if you have a chatbot, you need to be able to put guardrails around it that restrict what the agent is allowed to talk about with the end users. And so guardrails are also non-deterministic in the sense that they don't block the same thing every single time. So you do have to tune them. So a guardrail, what it does is it blocks the input and the output for things like PII, restricted topics, specific words. You can do regex patterns, all those sorts of things. And this will allow you to filter for input and output. So it's not just what you pass into the model, but it's also what it passes back out. So for example, even if my prompt was sophisticated enough to get passed to try to extract PII from the model, the guardrails in place should be able to identify that that PII is about to come out of the model and mask it before it gets to the user. So guardrails, Bedrock offers a feature called Amazon Bedrock Guardrails that I integrated with my agent, but you can use other providers as well. But the main thing is, this is the base level. You must be putting guardrails around your agent. And it's also like, it's a talent to tune these, because guardrails can often be overzealous and they will block things that are legitimate, or they could be too loose and they'll let through things that should not be let through. So it's better to be too strict and escalate to a human early than it is to be too loose and have a breach of some kind. All right, so let's go look at that. All right, so this is my basic agent, but the actual agent that I'm gonna show you today, and I have a demo for this as well, is a much more complicated. So if I just kind of zoom out, you can see there's a lot more code here than what we're gonna go through today, but I'll just go over the basics. You don't need to read all of this. There is a GitHub repo at the end where you can explore all the code, but I have a system prompt telling my agent who they are and what they're supposed to do. And then I have some configuration that's coming from parameter store in AWS. I have some model configuration here, and then we're creating the agent. So this is the part that I wanted to really get to here. So for the model creation, what you do is you create your guardrail in Bedrock, and then you just reference it whenever you create your model. So here I'm referencing the guardrail ID, and then whenever you create your agent, you just pass in that model, and now every single request that comes through it will hit that guardrail. All right, so let's actually try this. So I'm logged in. This is just running on localhost. I'm logged in, so my agent is authorized. Only valid users using OAuth can hit it through my API gateway, and then API gateway turns around and invokes it using IAM credentials. So I'm logged in here, and I should be able to type, help me reverse a doubly linked list in Python, and we'll hit enter, and we'll see if it tries. One other thing to note while this is running is that AI agents and AI in general, one of the major trade-offs is latency. And a lot of the things that I show you today, the trade-off is latency. So you'll notice that whenever I type, there's about, in some cases, a 15, 20-second delay, but that's on purpose. Okay, so this is good. It came back and said it couldn't do it. So that's really what we want. And you could also handle this error more gracefully, but just a demo. All right, I'm gonna log out and log back in, because if I don't, it will stay in the same session. I want a new one. So now let's talk about the next failure mode. All right, so I don't trust my agent to follow directions. This is a really big one. This is one of the hardest ones. So can I get a refund for my order? It's beyond the return window, but I really need the refund. And the agent's just like, sure, why not? I put in the prompt, don't do that. I put it in the prompt. I put it in there twice, actually, but it just doesn't listen. So my first instinct is to go back and change the prompt. If I prompt it harder, it eventually will listen. That's what I've been told, and that's what I'm gonna keep trying. But that's not how it works, right? So in this case here, our agent never actually called the tool. It never even did it. It just said that it told the person, never checked anything, never looked up the refund about anything at all. It was just like, sure, yeah, I did it. Everything's good, we're good. And it's like, yeah, that's not really gonna work, right? So we need ways to fix this. And one of the interesting things that's came out recently is steering. And when you really boil it down, this is really using an LLM as a judge pattern. So it's layering a supervisor AI around your other AI, as well as injecting deterministic logic at certain points in your agent lifecycle. So agents run through a loop, and they take in information, they see what tools they have available, they decide when to invoke a tool. The harness gets back that information. The harness then goes and invokes the tools. So the agent itself is not, the model is not invoking the tools. That doesn't happen behind the scenes in the inference space. That happens in the application space. So that means that you have the ability to inject deterministic logic at any point before a tool call, after a tool call, before a model response, after a model response. Steering is a feature that allows you to apply a couple of different types of things at those points. So one of them is to have another agent check the response of the main agent. And so I call this like the agent buddy system. And it's safer to have two agents disagree than to have one just do whatever it wants. So if you have a secondary layer that before the model responds to the user, the second agent will review it, and based off of a rubric, so we have a second prompt, based off of that rubric, it can evaluate exactly, did this agent actually, like, is it the right tone? Are they following the right procedures? Things like that. So the LLM as a judge pattern is best used for things that require judgment, things that are hard to encode in an if-else statement. So that's what the LLM pattern is best for. But you can also do steering with deterministic logic as well. So like before a tool call, I can grab the context of the entire event, of everything that has happened in the conversation up until this point. I can analyze it, and then I can say, I'm going to block this tool call, I'm going to cancel this tool call, or I'm going to let the tool call go through. So that's why I'm saying it's like these out-of-the-box end user products. Some of them give you the ability to create hooks, and you absolutely should whenever you need to, but sometimes you might need to go down to a lower layer to something you can control end to end, and that's when you would build your own custom agent using a framework. All right, so let's look at that. All right, so here you can see I have this plugin defined on my agent, and I have this customer service steering handler. And if we go look at the steering handler itself, I have a system prompt, that's the review policy. Like reject if I have unconfirmed promises, make sure you're not spilling any internal system details, over-promising on escalations, hallucinated contact info. So this agent, it has a fresh context window, but you can inject whatever information you want into that for it to analyze and reason over. And so this will, it will return either proceed, meaning it was approved, guide, so it will give guidance to the model and allow it to try again, or reject, in which case we can escalate to a human and just pull the parachute cord and go up to a higher level. So here we have our steering handler. And here we have this steer after model function. And this is going to go ahead and do the evaluation that we're talking about. So if I scroll down to, here we go. I create a reviewer agent, and this reviewer agent takes in that system prompt, and it will review it and then return that. So if I go over to my running agent, let's do the happy path, and then I can show you what the logs looks like, and you should be able to see that steering. So I can say, help me return order 1, 2, 3, 4, 5. And then while that's running, I've already run this a million times, so we can go check the logs. And if we scroll down, let's check this one. If I scroll up, that's not the right one that I want. Let's go back. Let's see if this one's done. It'll take about 20 seconds. Let's check this one. There we go. Okay, so if I zoom in on this and scroll down, first of all, you can see it calling tools. You can see what it's doing here. So this is saying, perfect, I've successfully generated your return shipping label, and then you can see the steering agent comes in and says approve. So if at any point that it came and it said something that was out of the bounds, it could throw that away and make the model try again. And you would set like a max tries, so that way the model doesn't burn forever, because the trade-off of this is more tokens and more latency. You've doubled the agent loop and you've doubled the evaluation tokens. But for critical things, this works really well. And we've done internal testing at Amazon that have shown that this has a significantly higher reliability rate than a pure graph-based or like an agent SOP prompt-based type of approach. Another thing you can do though is have deterministic steering logic. So this is another steering function that you can pass in. And this one is the refund workflow handler. And so what this does is it ensures that they've actually looked up the customer order and also that the customer order matches the amount that it's trying to return. So here we have steer before tool. So before the refund handler is called, I'm going to verify that they looked up the customer. If they did not look up the customer, I block it and I say you must look up the customer first. If I have the order history, then I can check to see if the refund amount actually matches the order, right? So this is just code, you can put whatever you want in it, but the underlying mechanism is hooks. All right, the next thing is I don't trust my agent with my tools and my data. So I think that this is an interesting one. Can you check the status of order 12345? And it comes back, oh yeah, sure, order 67890 was delivered to Morgan Willis and here's her address, right? So it's like, that's not good, right? Like I don't trust my agent to provide the correct values to my tools. My tools are accessing internal system information, like it's accessing databases, calling APIs, RAG systems, and I kind of don't trust that my agent is going to provide the correct input to those things and even bring back the right data. So how can you control that? Yeah. Yeah, so this could be a hallucination. It could be that it looked up the wrong order ID. But yeah, so this would be like an example of either hallucinating or worse. What was that? What is hallucinating? Okay, hallucinating is when an agent or a model, it's when an LLM makes up information and it responds very confidently, but is incorrect. So LLMs are not fact machines, right? They're prediction machines. And so whenever you feed it a prompt, it gives you the most likely response based off of its training data. And sometimes it gives you the wrong answer. And so I think that we're seeing hallucinations go down a lot in specific areas. But for businesses especially, if you have internal proprietary information, the models are not trained on that information. So how can you give the model what it needs so that it's able to give accurate responses without making things up? And that's really where the practice of context engineering comes in, which is where you give the model exactly the information it needs at the right time so it can make the right decision and make the right response. So there's a couple of different levels to hallucination. And this particular solution I'm going to show you is more about trusting the model to use the tools correctly. There's multiple ways that agents can use tools incorrectly. They can call the wrong tool entirely. They can pass the wrong inputs to the tools. But if it calls the wrong tool, it can actually call a chain of the wrong tools as well. So what tools you expose to your agents really heavily impact how performant it is, because agents can generate tons of tokens and consume a lot of tokens by calling many, many tools. And so the more tools you expose to your agent, the more likely it is to call the wrong one. And you also need to design your tools carefully, which we'll get to in a second. All right, so the problem with this scenario is that the agent controls which values go into the tools. It controls the parameters. And agents do hallucinate parameters. I've seen this happen with this exact example. So the reason why this is in this slide deck is because I've seen it with this example, where I say, hey, look up order 12345, and it looks up order 23456, things like that, where it's off by one. Even though I just told it what the order ID is, it's still turned around and used the wrong value on the back end. Right, so that's a huge liability, that's a huge risk. So the fix for this is actually running MCP interceptors in between your agent and your tools. MCP allows you to expose tools to agents, And there are many ways to expose tools to agents. You could just expose them locally. Like you could just package up a tool with an agent and have it all do everything locally. You can give your agent just access to a shell. You could just give your agent access to a code execution environment where it just writes its own code. It creates its own tools on the fly. These are the things that people are doing, but I do believe them to be quite forward-looking for certain applications. Like a customer service application, that's not something you should do. You should constrain the tools in multiple ways. And one of them is to use MCP, because MCP, it decomposes the tools from the agent. So now I have a space where I can put something in between them. Right, so that decoupling motion allows you to put a proxy in between. And now you can inspect every single tool call that comes through your MCP server, and you can block them dependent on the context of what's going on. With the case of looking up an order ID, you should never let your agent supply sensitive parameters at all. Don't even expose it as an option to the model. So whenever you expose a tool to an agent, you define a tool schema that says, this is what the tool can do, here are the parameters, and this is what the output looks like. The agent then provides the parameters. Don't provide the sensitive parameters at all, just hide them. And then the parameters, they need to come from the system. So whether it's environment, config, the user token, things like that. You want to get those sensitive parameters, secrets manager, whatever it is, you want to be pulling those from a dynamic place instead of allowing the agent to supply them. And you can do that using something like a Lambda gateway interceptor. So I'll show you some code for that. All right, so it's actually not in my agent code at all. My agent code has no clue this even exists. This is just a part of my architecture. And so what I want to show you here is the handler. So this is a Lambda function. Lambda is just a function as a service that I stuck in between the agent and the MCP server, and this runs deterministically on every single tool call. And so what this does is it takes in an event and a context, and it has access to the user's token. And what it does is it extracts the user name, the customer ID, from that, and then it actually will inject that into the tool call. So down here, I return this transformed gateway request, and that includes this authenticated customer ID. And then in my Lambda function, where it actually invokes the tool of looking up the order, I pull that authenticated customer ID, and this actually is different than this one. So this, if this came from your agent, like if you expose this to your agent, this could be whatever the agent gave you. And so if you were to run this test yourself, like in your own account, you could test both ways and like let your agent do it and then supply it and see if it ever gives you the wrong one. Because I actually did see that a couple of times, which was interesting. And it also totally depends on the model you're using as well, on how much these things will or won't happen. Models have different tool use properties, and some are better at using tools than others. All right, so another fix for this is tool design in general. Your tools should enforce strict validation of inputs. So you shouldn't just trust whatever comes in as input. You would treat it like a web form, you know, like an external user is providing information that you need to verify. Sensitive values come from the system, and also avoid open-ended interfaces, like run SQL query, right? So like in regular applications, we use parameterized SQL queries for a reason, right? So it's the same type of thing here. You want to make sure that you are using parameterized SQL queries and that you are not allowing destructive actions against your data where you cannot tolerate destructive actions. Again, it's really dependent on your use case, on how much risk tolerance you have for any particular system. And then the other thing here is to implement least privileged access for tool scoping, which we'll talk about in a second as well. All right, so another problem. I don't trust my agent with high stakes transactions. In this case, can you refund my order? It's over $899, and they're like, yes, sure. But the problem is that my company has a policy that if the order's over $500, I need you to escalate to a person, and it didn't do that here. So I gave it access. It has legitimate access to the refund tool. It's a legit thing there, but I don't want it to be used under specific circumstances. So we need deterministic rules to block this tool call. We need a guardrail. And one thing you can do is to have another type of policy or proxy that has a policy enforcer. And this policy enforcer would be able to determine who's calling the tool, what are they doing, and under what conditions, and you can evaluate if you want to block that or not. In AWS world, we have a service called Agent Core Policy. So in my architecture, my agent is running in a hosted runtime, Agent Core runtime. It sends a request to this MCP server. I have the Agent Core Policy sitting in between that's doing a policy evaluation there. And that's on top of the IAM policy of like, does my underlying environment have the AWS credentials to call my gateway? This is a secondary level of where I'm evaluating, does the agent have the access to call the tool, not necessarily the runtime. All right, so that looks something like this. This is a CEDAR policy. CEDAR is an open source policy language, and you have this ability to have this like declarative way to express your authorization language, and this keeps your authorization language out of your code, which is important as well. So again, my agent doesn't know anything about this, but it does exist in my architecture, and it's a guardrail that will stop my agent from doing something stupid. So in this case here, we have the refund tool, process refund, and I only want to allow it when the input amount is under $500. So if we go back to our demo here, which we can see our first happy path did work. Let's go ahead and do another one. I'm gonna say, help me return order 9999, one more 9, which is an order that is over $500. And this should come back and block it. So as this is running, this is going through a whole architecture where it hits my agent loop starts up, sees the tools, it's looking up my order information, it's calling out to the MCP server, that's hitting my gateway interceptor. The interceptor is injecting the customer ID. That goes and executes that, brings it back. Then it calls a knowledge base. What's the company policy for returns? Let me look it up, let me make sure. It checks the eligibility for that return as well. And then it goes to return it. But the problem is that this is actually outside of the scope of what it's allowed to do. So what it does is it creates a case, and this will ultimately elevate me to a human in the loop who can then handle the specific request. And this is handled at a deterministic level. All right, so now another thing here is that you need to be able to see what your agent is doing. So observability is more important than ever, especially because these are non-deterministic systems. So it's really hard to debug what went wrong if you don't have visibility into every single step that happened along the way. So observability, I think, is something that's always been hard to do, especially for distributed systems. And it's more important when you bring AI into the system. So where you can have auto instrumenting just turned on to where your developers don't need to do it themselves, I would recommend that. So that way you're not missing things right when you need it. You know that the data is going to be there when you need it. You want to use this to be able to pinpoint what went wrong. And again, the answer is not always going to be prompt harder, right? The answer might be add a new element to your architecture entirely. And the other thing is you want to set up anomaly detection where you can. So if for some reason you see an agent, normally there's a tool request volume of 100 in an hour, and suddenly that's gone up to 2,000 in an hour, right? That could be indicative of somebody trying to attack and abuse your agent. So you want to have some sort of anomaly detection in place on some of these metrics as well. And a lot of these metrics will probably be custom ones that you create. So I think that creating AI agents, custom AI agents that you control end to end, it's a real AI engineering effort. There are no silver bullets in this space. And I think that a lot of people want silver bullets, and AI can be sold as a silver bullet. And though I think it's extremely capable, and I use AI every day for all sorts of things, to build systems that run with any amount of autonomy, that have access to real data, that carries real risk and liability, you have an engineering project on your hands. And you need to make sure that you have visibility into what that agent is doing at any point in time. All right, so this is the architecture under the hood of what I've been showing you. And there's a lot of components that we didn't talk about. And I think that this kind of comes back to the idea of the old lessons still apply to the AI agent space. So I architected this agent in the way I would for any sort of application. We treat agents the same way that you treat any application you put on the internet. But if you've ever done like an AI agent tutorial, what it's going to show you is you create your agent, you deploy it, and then you hook a browser directly into it. It's like literally every single agent tutorial plugs a browser directly into your backend. You should not do that, right? We need to have all of the layers that we would normally have for any application. So let's walk through some of them. All right, so we have our web application firewall. The web application firewall is going to be able to shed load under specific circumstances. So you can block, you can have all your filter policies and things like that, but you can also set up like rules for bots. A lot of the managed web application firewalls like AWS, WAF, has a bot rule. So if you have a flood of bots coming to abuse your agent, then it can shed that load automatically. And so I think this is really important because with AI, we used to have like denial of service attack, and that still exists. But with a lot of hosted services, they're good at finding those, and you can shed that load, but also the managed services can scale up really big and absorb. They can absorb it. And so really what you have is a denial of wallet attack, where you have to pay for the scale that was brought upon you by someone else. And that's actually a bigger problem in AI because it's not just the scale of the compute and the memory and the network in and out, it's also the tokens. And the network in and out can get pretty big when you're talking about tokens and data generation. So you have to set up rules to shed that load. You have to have a place to formally do that. And you also want to make sure on your inference provider, so like for Bedrock, these different models, you can set like a max tokens response. And we have all these other layers that are in place, like the guardrails that we talked about. All right, but at the first level, we have the client logs in with an OAuth provider, and then we take that token, we send it through AWS WAF, it might get dropped there. Then at API Gateway, your API Gateway will validate the token. Is this an authorized user? You also have rate limiting set up at your API Gateway, so you can rate limit specific people. That's super important. After that, then you invoke your agent. This agent runs in a isolated runtime. Every session has its own file system, sandbox access, and so that way if I have multiple users hitting the same backend, they have isolated sessions, and those sessions don't have access to each other. So you want to make sure you're using a runtime that handles that for you, so you don't have to set it up. Agent Core Runtime has a lot of that stuff, but the other thing that's really nice is that it actually injects the credentials into the environment. So in this case here, my client used OAuth to log in, but API Gateway invokes runtime using IAM, which is a different authentication method. And that's important as well, because without that, my client has an OAuth token. This validates the same OAuth token. So if I have this endpoint, my client can just bypass all that and go directly to my runtime, and then I've skipped the protection layers, right? So those are the types of like threat modeling to think of whenever you're starting to deploy agents, especially because of the cost and liability aspect for these things. So once my agent gets invoked, it has access to the guardrail on the model. So that's one of the first lines of protection. We have the multi-agent steering. So one agent is reviewing the other agent. And we also have the deterministic steering driven by hooks. After that, we then try to invoke tools. That will go through the CEDAR policy enforcement. Who's calling the tool, under what conditions, should I allow it or should I deny it? Then the MCP server has the interceptor. That's just code. You can put whatever code you want in your interceptor. I chose to inject the order ID into my tool, but that could be anything. It could be custom authentication logic. It's just business logic, extra verification, extra steps. It's up to you what you put in that, but ultimately, that's just code that runs on demand for every tool call. And then we have our tools in the back, which are going to be designed with a specific scope in mind. They have their own parameter validation, and we're following all of the normal best practices for building web applications, right? So this is where it's like the old architecture lessons still apply, plus a few new ones to deal with the AI-ness of it all. All right, so a layered approach to trust. There are multiple dimensions to trust, like the prompt. The prompt is, the risk is the instruction hijacking. So what do we have for that? Is guardrails. But the thing is that that's probabilistic in nature. So you want to have both deterministic and probabilistic guardrails in place. Tools, unauthorized or dangerous access. You want to have tool authorization in place. You can also use agent steering to block those things. Ultimately, I would say you probably want to do both. Your runtime should handle shell access. It should handle isolation. Your data. This is Again, the guardrails are a good one. Tool design is important, and steering, all of those things can capture data exfiltration before it hits your end user. Network, we didn't talk about network, but whenever you deploy your agents, you want to deploy them to a place where you can set up all of your same sorts of firewalls that you would, again, for any other application. So in the case of Agent Core Runtime, you can deploy those inside of a VPC. Once it's inside of a VPC, you can set up VPC endpoints, you can set up security groups, you can set up NACLs, right? So it's like, you wanna make sure you're deploying your agents to an environment that gives you all of those different configurations. And then identity, you wanna use least privilege for any workload, right? All right, so trust is not something you give to an agent, but it is something that you build around it. And this is the QR code for all of the code, everything that we covered today. If you wanted to pull it and take a look at it yourself, feel free to do that. And if you want to connect with me, if you just Google Morgan Willis Cloud or Morgan Willis AWS, my LinkedIn will come up. And I'm very active on LinkedIn, and I'm happy to answer your questions there as well. But we have some time here to get questions now. So does anybody have questions? Yeah. Yeah, so, right, that's interesting. So I think that the idea of, yeah, well, I think that the thing is like, it doesn't cost money until it does. You know what I mean? And then it's like, I feel like it's like, that's a very reactionary policy. I do think, again, it depends on the specific use case and the risk profile of that. So what is the worst case scenario that's going to happen without guardrails in place? Like, does the knowledge base that you're connected to, does it have access to private information? Is it, does it have access to information that shouldn't be leaked, or does it have access to tools that can be used inappropriately? I think can it leak system details internally that someone can then use and turn around to do something more malicious? I think those are the types of questions that you have to ask. And if it's not having any of those problems, then maybe you do a cost comparison. But I think that the real thing that I would dig into is like proactive response versus reactionary response. And we don't want to wait until something goes catastrophically wrong before doing that. So that's the angle I would take. Yeah, good luck. All right, any other questions? Yeah.
I just find it really interesting that the steering like, it's just fascinating to me how even with the release whatever they want. So it's just interesting how one has presumably the same rules, just where it's like it's hard to understand why they do what they do.
Right.
If you took the steering agent's code and put it in the original, still go off the rails. Like,
So it's such an, I totally agree. It is bizarre, right? It's like sometimes I saw someone post the other day, it's like, adding more AI to your AI is not the answer. And I'm like, sometimes it is, actually, like weirdly enough. But the thing is that they're both non-deterministic in nature. So the thing is that it's not that the agents don't follow directions 100% of the time. It's the problem is when they don't follow the direction the 2% of the time. That's the problem. And so I think, or even more than that, 10% or whatever it is. But I think that this is one of those things where, like, in a demo environment, the agents may follow the instructions, but once you put it out into production, that agent just falls apart. And part of the reason for that is because of all the varied input, but also it's because you're running something at scale. So like you're gonna hit that 10% of the time where it just doesn't follow the instructions. So agents fall victim to this thing called the lost in the middle effect, where they pay attention mostly to the instructions at the beginning and at the end of the prompt, and they tend to lose what's in the middle. And so the longer the conversation history goes, the less likely they are to follow your instructions. And so I don't know if you've seen this, but with like a lot of end user facing chatbots, one of the ways that people get them to break out of their guardrails is just by talking to them for hours and hours and hours on end, to where your context is enormous. And then finally, then you ask the thing you want to ask. And then it'll do it, even though it's against their rules. And so it's because it loses track of the rules at a certain point. So this new steering agent has a fresh context. So all it sees is like the most recent user query and the response. And it depends, you can control how much it sees. So that fresh context window can be helpful for it to not be clouded. But the other thing too is like, it's less likely for both agents to not follow the rules at the same time than it is for them to do it together, especially if one has system instructions to where you're telling it to evaluate the other. And you can use different model providers completely for different parts of your system, like for multi-agent architectures. So that way you don't have, the models can be biased based off of their training data, and they behave differently. So if you use different model providers for different agents in your system, it acts as a bit of a better system of checks and balances. But again, I would say that some of this stuff is like an art more than a science at this point. Yeah. Yeah, so the steering agent is created from scratch for every invocation. So it gets wiped for every single invocation, but it is just code. So you can kind of do whatever you want with it. So you can expose, like whatever you bring into the system prompt is one piece of information, but then after that, you can choose, like there's like a message history and an event ledger in the context of the agent, and you can choose specifically like what you want to bring into context. Do I just care about the final response? You know, like I don't really care how many turns you took and what tools you called to get there. All I care is in the final response, you're not allowed to say X, Y, Z. So in that case, all I have is the system prompt and the final response, none of the conversation history. So, but you can change what you do with that. Yeah. All right, I think that that's all the time I have for questions here, but feel free to come find me after and we can chat. And like I said, you can find me online and we can chat there too. All right, thank you.